All right, so the next problem I want to work looks like this. And we started with a point load, and now we have a uniform load, a constant load, and now we have a linear load. So let's just see what that will pose to us. So again, I'm interested in knowing the value at C. So again, I'll make my little cut here, and I'll look at the left side or the right side. Now, if we look at it from just finding reactions, from that point of view, you're going to have to find a reaction at A here or a reaction at B there, so really no advantage. But there is a marked advantage in looking at the loading. If you look at the left-hand side, you have a triangular segment. If you look at the right-hand side, you have a trapezoidal segment. It's not hard. I don't know. I know the area under a trapezoid. I can figure that out pretty quickly. What I can't remember is where's the centroid of a trapezoid. That I haven't memorized that one yet. So the typical approach then would be to break it up into two forces, a rectangular component and a triangular component. And that you can do. And there may be some situations where you have no choice. You're going to have to look at it as a trapezoidal load. In this case, you do have a choice. I think it's going to be a lot easier to deal with the left side, so I'm going to do that. So that means I need to find my reaction at AY. So again, I'm going to draw a free body diagram of the structure. And I'm going to assume a reaction at AY and one at BY. And now I have to resolve my triangular load into a concentrated equivalent. Well, it's still pretty straightforward because it's a triangle. We usually know the area of a triangle. It's 1/2 the base times the height. So 1/2 18 times 3 is 27. Does that sound right? Yep. Am I getting a yes?
Yep. Yes, sir.
Oh, well, you don't have to put the sir in there. But thank you for the yes. The other thing I do remember, you probably will too, is that the centroid of a triangle is usually 1/3 the distance from the larger end. So 1/3 of 18 is 6. It would be 12 feet from the smaller end. Still, that's enough information for me to now find my reactions. And again, I'm only looking for the reaction at A, so I'm going to sum moments at B. So I'll assume hand rule, and I'll sum moments at B. I guess I got that pork thing on the brain still. Right hand rule. So about B, my load is creating what kind of moment? Positive or negative? Play along. Oh, you guys already zoned out to the fuzzy cat videos, didn't you?
Positive.
Positive, thank you. So that's 27 kips times a moment arm of 6. And then the reaction at AY creates what kind of moment? Negative. Moment arm of 18. So I should be able to solve for AY. I think AY will be 9. Is that right?
Yes, 1/3.
1/3 of 27?
9.
9. Okay. Cool. So now I'm going to look at this left-hand side. I'll make it a little bit larger so we can see it. I will put on the reaction I just found, which was up. I assumed up and got a positive answer, so it is up 9 kips. I'll just go ahead and sketch in the triangular portion of that piece. Come back to that in a second. Well, let's do it now. So what is the intensity? Oh, I'm sorry, this is 6 feet length. So what's the intensity of the load here?
1 kip.
Yeah, it's a similar triangle, right? So I know at 18 feet it's 3, so at 6 feet it should be...
1.
Yeah, 6 is 1/3 of 18, so 1/3 of 3 is 1. And once I know that, I can find the concentrated equivalent of that. So this little triangular piece is easy to find. 1/2 base 6 times height 1. That ends up being a value of 3. And where is the centroid of a triangle? It's 1/3 the distance, but from the big end, and 1/3 of 3 is 2 feet. That takes care of that. And then now I'll assume my positive shear force at C and my positive bending moment at C. I did not put the axial force because I'm not interested in it. Plus, you can probably see that there is no axial force. There's no horizontal forces in the structure at all. So based on that, I can now make sure this free body diagram is in equilibrium. So like we've been doing before, I will sum moments about the cut surface. That will make sure that the shear doesn't create any moment. And using right-hand rule, this kind of moment is positive. About the cut, the concentrated equivalent force creates what kind of moment? Positive. So the force is 3 kips. The moment arm is 2 feet. The reaction force, 9 kips, creates what kind of moment about C? Negative. That's 9 kips, and the moment arm is 6 feet. So you should be able to solve for the moment at C. It looks like it's going to be positive. It's going to be 48. No? Is it 48? Yes. And the units are kip feet. And it came out positive, so I have a positive bending moment. Does that make sense?
Yes.
Yeah, if you go back and look at your problem, it won't be symmetric, but you will get that kind of happy face curvature all the way through the structure. So positive bending moment seems reasonable. It won't tell you if you got the right number, the magnitude, but at least tell you if the sign came out. If you did get a negative there, it's time to rethink that maybe something didn't go right in your equation. And to finish this off, we will sum forces in the y direction. And I'll assume up is positive. So I've got the shear force VC is down, so that's negative. My concentrated equivalent 3 kip force is down, negative. And my reaction force is up, so that's positive. So it's not a hard equation to solve for. It looks like it's going to be 6. And we're done. Any questions about that one? Cool.